Okay, hello class. How are you so far? So we will be dealing with the chapter 7, which is related to the shear. We call that transverse shear. That's what we'll be exploring in this chapter. This is an interesting chapter. It's continuation to what we have learned in the previous chapter, which is chapter 6. So listen to this carefully. You have to follow each and every detail very carefully. So any questions that you have during the process, we will discuss this when we have common meeting time. That means you can email me always. A couple of students already emailed me, and we typically meet in MS Teams. We set up a time and we meet during this MS Teams. And the other thing is, the first part of the chapter, I will deal with derivation. It's important that you know how to derive things, not only for mechanics of materials, but for different other subjects that you take. It's important for you to understand the derivation behind a formula. So almost the next 30 minutes, 30, next 30 minutes would be deriving the formula, which is shear stress is equal to VQ over IT. I'm waiting for the software to sync, the OneNote to sync. Anyways, it'll sync in. Yeah, this is the formula. So the VQ over IT. So this is the formula that we will derive. And bear with me for 30 minutes. It's important that you know how to derive this. Okay. Now, what we have seen in the last chapter is flexural formula. If you remember, it is sigma equal to negative my over I. I hope you still remember this. It's important you remember this, you understand this, because in the midterm 2, you will be required to use this formula a lot. That sigma is equal to negative my over I. So what is the meaning of this sigma equal to negative my over I? Is that when we have a beam and we give a bending moment m, due to this, we calculated what is the normal stress sigma due to m, because we came up with a theory saying that this is acting as if, that means due to the moment, what happens? The beam bends like that. That means the bottom part is in tension, the top surface, this surface, is in compression. So we assumed as if that there is a regular beam which is undergoing compression in the top part and tension in the bottom part. So we thought this is tension and this is compression, and compression slowly reduces to the point where we call the neutral axis, right? So this eventually reduces and slowly the tension increases on the bottom surface. So we came up with this theory saying top part is in compression, bottom part is in tension. That means the top part, if we zoom in the top part, the top part is in compression. Let's say this is the neutral axis. That means the length of that axis does not change. So that means it is getting compressed and the bottom part is extended. That means you have tension on the bottom part, right? So this is compressive stress acting on a small area dy, isn't it? This, let's call it dy, acting on a small area dy. So this is a function of y. So if we want to know what is the total if we want to know what is the total force or the net force acting, we have to do sigma of y, which is a function of y times dA, and we have to take an integral, and then we get the force. We get the force. So one thing that I want you to remember and understand is stress is a function of y. That means if this is the beam, if this is the beam, and let's say this is x, so this direction is y. That means sigma is a function of y. So to be more, we have to be more careful here. Y would start measuring from here, from the neutral axis, right? If you go up from the point neutral axis, you get positive y. If we go down, we get negative y. Agreed? This is what we discussed in the previous chapter. So the purpose was due to the presence of moment, how much would be the bending stress? That would be this much. That's what we discussed last time. Now, in this chapter, our idea is what is the effect of shear? That means, see, these are the objectives for a beam. We will identify what is happening for the shear stress. For example, if you look at this beam, when we keep increasing a load, let's say we have a pin joint, let's say we have a roller joint on the right, let's take a beam and let's have a pin joint on the left and roller joint on the right, like that. And let's apply load P. What happens due to that? As we keep increasing P, we get a crack. And then it breaks, right? It breaks like that at some section, isn't it? Isn't it breaking like that? Slashing off like that? That means it's becoming two parts. Isn't it acting as if we are taking a knife and slicing it off? That means isn't it acting as if there is a shear force? Because we made a cut, we have to draw equal and opposite. Shear force going down on the left side, shear force going up. Isn't it acting as if there is a shear force? So how much is, let's say we get V, what is the shear force at certain cross section? How do we get the shear force? From the shear force and bending moment diagram. Because from the original beam, we can always draw shear force and bending moment diagram. That means if we have to draw, we draw something like this. Remember, this is the shear force, and bending moment diagram is something like that. Something close to that, isn't it? That means where is the shear force maximum? It is maximum here. That means at the leftmost or the rightmost edge. That's where the shear force is maximum. Would you agree to that? For that given loading? So in the previous chapter, we already discussed if there is a maximum bending moment, that means exactly at the center, in this case, in this type of loading for this beam, this is the bending moment max, the maximum bending moment. What happened to normal stress? What happened to sigma? That's what we found out. So in this class, due to this maximum shear stress occurring at the edges, due to this V, what happens to tau? Tau is what? Shear stress. If you remember, tau is shear stress, sigma is normal stress. This is normal stress, and this is shear. Okay, what happens to that? So we have to derive that. It is not that straightforward like we say V is nothing but, sorry, um, if you remember, shear force over area is stress. You may think that is that simple. If we just know the cross section of the beam, that means if we know how the beam's cross section is, let's say, if we know the beam's cross section to be A, you may be thinking, oh, it's nothing but V over A. You'd be getting tau. On a crude manner, yes, you're right. But if I were asking you from this part, if we zoom in this part, let's say this is how the cross section is looking like, and I'm asking you, hey, what is the shear stress at that point? What is the shear stress at the center? What is the shear stress at the edge? Shear stress. What is the shear stress at this edge? In that situation, we can't apply this formula. We need something more. And that's exactly the purpose. To calculate the shear stress, sorry, to calculate the shear stress at each y. Where is y? If you remember from the previous class, at the neutral axis. Let's say the neutral axis. And going up is positive. What is this? Shear stress is a function of y. And who told you that the cross section will always be rectangular? It can be circular, it can be elliptical, it can be looking like an eye, where eye is, I think, one of the most famous cross sections. And if I were to give something in the exam, I would prefer giving you an eye, because in all building materials, majority of building materials, it's eye cross section. Look at railway tracks. I think I remember the picture. Railway tracks, if you observe, a railway track cross section looks like, almost looks like that. The rail track cross section, right, on which the train wheels are placed, it looks like an eye. Eye is a pretty important cross section. So if for eye cross section, what is the shear stress at this point? What is the shear stress at that point? Because we need to know shear stress at each and every point so that we can come up with a proper shape, proper material. Now that I motivated you enough that we have to come up with this equation, let's jump into derivation part. Let's jump into the derivation part. This is something we have to understand. Okay, let's take a beam. Okay, let's take a beam. And there are, let's say there are different loadings. Let's say there is this distributor load. Okay, and let's say there is a bending moment. Some bending moment. What I want you to do is we have to come up with the formula for V at certain cross section. That means when we make a cut somewhere here at certain cross section, and in this cross section, because this cross section is a function, the length is a function of x, longitudinal is a function of x, and because let's say there is a neutral axis, that means the centroid of the cross section. From the centroid of the cross section, going up is y, where, by the way, we have to be careful. This is the beam. That's the beam. Okay. So at a cross section, we have to come up with the formula for shear stress as a function of y. So we have to make a cut. Let's make a cut. So let's take a small strip like that. Let's take a small strip like that. That means we are not making one cut, but we're taking two cuts, isn't it? We're making a cut here, we're making another cut there, right? So what should we do when we make two cuts? First of all, let us take the cut part. That means I'm going to take the part that has been cut, right? This is the part that has been cut. This is the part. So because the longitudinal direction is X, because it's a thin strip, I'm going to name this as, this will be delta X. This is delta X. Okay. Then when we make a cut, what are we used to? We are used to drawing normal force, shear force, moment at every cut. That means here, I'm going to draw normal, I'm going to draw shear, I'm going to draw moment. Here it's a normal, it's a shear, it's a moment, right? Because we made two cuts, we have to give all these things. And remember, we have distributed load here, right? That distributed load, let's call it W of X. If W is constant, that means if it's a uniform distributed load, it's just W. But W of X means distributed load is a function of X. That means it can be distributed load can change at every value of X. You can have 2 kilonewton per meter at 2 meters from left side and 10 kilonewton per meter at 7 meters from the left. So that's why I said distributed load is a function of X. So this is the shear force V, and this is the shear force V of X. Let me write it, V of X. And this is the shear force, which is V of X plus delta V, isn't it? The delta V is because if this is V, it can be plus or minus V. The shear force changes, isn't it? If you look at this, picture here, the shear force at every X is different. It can be more or it can be less compared to certain point. That means at this point, it can be V. At dx, it is slightly different, right? That difference is what I'm assuming to be delta V. What about moment? It's the same. If I assume that this is moment at X, I'm going to assume that this moment is moment X plus small change in moment, dm. And this is the normal force. Because our major interest is, this is the normal force at X. Our major interest is X plus small change in the normal force, and this is the normal force at X. Supposedly both have to be the same. So what I have to do is I should exactly say normal forces, because they have to balance one another. Our major interest is basically in V of X plus delta V. So what I'm going to restrict my discussion uh, to only V of X and the contribution of M towards shear. Or sorry, towards normal stress. So what we know from previous classes, sigma is M negative my over I, right? That's something we know from previous class. So we will use M and we will represent something in terms of sigmas. Okay. So first of all, let's do one thing. Let's identify where is the centroid of the cross section. That means let's identify where is the centroid of this cross section. Let's say this is where the centroid is. For example, that means the centroid is like that. So this is the point where we have the centroid. Okay. So moment is acting with respect to this axis, isn't it? If we call it x, this moment is with respect to this axis shown. Okay. Just that you identify. All right. So let's name this thing. Let's name that this is the centroid C. Can you tell me what are the sum of moments with respect to C? That should be equal to 0 because it's an equilibrium. So with respect to C, would you agree if I told you that that implies is nothing but V of x times delta x and it's negative. This V of x times delta x because this is delta x away from the point C. So, and it is clockwise, right? It is clock because it's going like that with respect to the centroid. Okay. Minus, so this is negative V of x times delta x, right? Next, negative M of x. I'm talking about this one. I'm talking about that one, negative M of x, because it's going clock with respect to C. Then what about this W of x? Can't we write a single equivalent load which is nothing but W of x times delta x over 2. It's not over 2, actually Wx. And that is the load, and it is acting, at, what is that? Isn't it delta x over 2? It is half of delta x. So, and it is counterclock. So I'm going to write it as this is W of x times delta x times half of the distance from C, which is half of delta x, right? Half delta x, what I mean is this one, half delta x. So this is how it is trying to rotate. So what I'm trying to say is this distance is half of delta x. Anyways, that is positive. And don't forget this one here. Don't forget that, which is counterclock. So it is positive. So that means I'm going to write it as plus m plus dm is 0. So let's, by the way, this I have to write it as not m plus dm. I have to write it as m of x plus dm is equal to 0. Okay. So negative m of x, positive m of x cancelled out. And then what we have here? We have that implies we have negative v of x delta x. Then we have plus wx delta x square over 2 plus dm is equal to 0. So what can we write? Can I write this as v of x delta x is nothing but dm plus wx delta x square over 2. If I rearrange this, and let's take limit delta x goes to 0. What it means is we are taking a very thin strip. So this delta x should be so small. So I'm taking it to be so thin. So this delta x square will be going to 0. That implies we get v of x is dm over dx. It no longer becomes delta x. Limit delta x tends to 0, we get a smooth function. Remember, this is an important thing that we require. This is something that we require in a little while. So let me Let me select it. Let me box it. Let me, highlight it. Then we are not finished with the discussion. Now, let me select this part, copy, paste. What I will do is I will bring this to the bottom. So you remember this discussion that we just made? This cut that we made? Okay, so we will deal with this cut now. So I'm going to keep everything the same except this, because anyways n of x has to balance, and I'll slightly move this v of x plus something a little far away. What I want you to observe is this cross section. So in this cross section, because our idea, let's not forget our idea. Our idea is to find tau as a function of y, as a function of y. That means if the centroid, like if this is where the centroid is, for example, this is exact point where the centroid is, from this going up is y. From that point going up, that is y. Okay, it's going down, that is negative y. Okay, so we have to make a cut. You may be wondering, oh, isn't this already a cut? Isn't this already when we made a cut, when we made a thin strip, isn't that what we got here? Yes. To this thin strip, we again make a cut horizontally. Before we made a cut vertically, so we make a cut horizontally. What I mean horizontally is like this. We make a cut like that. The reason we have to make a cut is we need to get tau as a function of y. That means we need to make a cut somewhere along y. Okay. Before we make a cut, let me ask you a question. Due to this m plus dm, didn't we in the last lecture come up with the formula sigma is my over I? Yeah, it's a negative, by the way, negative my over I. Yes, we did. That means sigma is a function of y, isn't it? It's a function of y. At each y, you have a different sigma. That means here, you have maximum sigma. Remember, it's a compression. So by the time it goes to the centroid, the sigma is lower. It becomes smaller, smaller, and almost goes to zero. But here, the sigma is tension. That means as it is closer, zero. As it is closer to the centroid C, it is zero. But as it goes to the edges, it becomes max. So what I'm trying to say is when you take this cut, when you take that strip, when you take that, that means let me redraw the strip. What I'll do is I will take, because I made a cut, sorry, and this is, and then there is a cut, this is a cut, let me make cut here. Only that is a flat edge, and that is a flat edge, and this side is a cut. So on the bottom, what I'll do is I'll draw with this color so you understand that I made a cut there. Understand? So I am taking the part that I made a cut. So in this part that we made a cut, as soon as we make a cut, what are we supposed to do? Normal reaction. Then for this cross-sectional area, there is a shear force acting, right? Or shear stress acting over that area. isn't it? And by the way, never forget the dimensions. This is dx, or delta x, and what is this supposed to be? That is supposed to be the thickness, t. It may not be constant. If it's a rectangular cross section, thickness is constant. But what about I cross section? Thickness is not a constant. It's t. Let's keep it t. That's the thickness. So that is tau. And remember, this is sigma. This is sigma as a function of y. That means the sigma can be different as we uh, so the sigma can be different at each point. Let me bring it. The sigma of y, sigma can be different at each point along y, right? Then what else are we missing? We are missing the sigma on the right. Let's call it sigma dash. Sigma on the left. Right? Sigma on the left to be sigma, which is a function of y. Now what else do we have? We have, and why did we get the sigma? We got the sigma because of m plus dm on the right side, and this sigma is because of m on the left side. So I'm replacing m. If you observe here, I'm not drawing this m any longer. I'm not drawing this m plus dm any longer because I'm replacing the effect of moment with the stress, here. Okay, then for this, we're almost there. We're almost there for the derivation part. Then what we have is actually we have everything. So this on the bottom is the normal at some y because we made a cut at y, and we don't care about this normal at this point because what I'm going to make you do is take sum of forces in x direction equal to 0, assuming that this is a x. What do we get? We get, because we are balancing forces, and what I drew here is the stress. What I drew here is the stress. So how do you convert stress to a force? You multiply that with area. So sigma y, because it's a function of y, sigma of y on the left hand side times dA. Why am I writing dA? Because sigma is different at each point, so we have to take area integral so that we get what is the total force. Let me use a different color, and let me use which color? Yeah. So the total, that is sigma of y times dA integral. Okay. Similarly, what do you get on the left hand side? What do we get on the left hand side? We get the same thing. Due to the sigma dash, we get integral sigma dash of y times dA. We have to take area integral. Okay, so when we take sum of forces in x direction equal to 0, we get this going right, minus integral sigma dash function of y dA, because this is going left, right? This is positive x, and this force is going left. And what else? If you observe closely, we have a shear, because we made a cut, remember? So how much is that? Is nothing but plus shear stress times area. Area is nothing but delta x times t, isn't it? This cross-section area on which shear stress is acting is shear stress times the area on which it's acting. The area is nothing but delta x times t. Now this has to be equal to 0. We're almost there. We're coming closer. That implies, no, yeah, delta x times t equal to 0. Yeah, we're coming closer. That implies, what is sigma dash y? Isn't it m of x plus dm times y over I? Now, this is the careful part that you have to really understand. You know that sigma as a function of y is moment a function of x, because at each x you may have a different moment, right? Right? When you make a cut, you have to go back here. When you make a cut at this section, uh, when you make a cut at that section, which is at x from the left hand side, this is at x, so this is at x, and this is at x plus dx. So this is moment x plus dm, so this is moment at x longitudinally. But what are we getting? The sigma is a function of y, which is moment at that cross section times the y position along the y position with respect to the centroid of the cross section, where the cross section would look like that, right? So from this centroid, it depends on which point we're considering. Y over moment of inertia of that cross section, and it's a negative. So what is this y? The y is the distance measured from the centroid along y direction. This is y. And what is moment x? Moment x is moment at that cross section. Take time to understand that. You have to really understand this. So when you go over to this part here, we know what is sigma y. It is moment at that cross section times exactly which y we're talking about. By the way, this is negative, right? Exactly at which cross section, at which point above neutral axis we're talking about. And what is this I? I is moment of inertia of that cross section. Okay, assuming you agree to that, what about sigma y? What about sigma y? You would say the same thing, which is sigma y. Sigma of y is moment at x times y over moment of inertia of that cross section. This is negative. Let's plug in the same thing here into this equation. So when I plug in the same into this equation, I'm going to get minus m of x y over I dA. This is integral minus integral of minus of m of x plus dm over I times y dA plus tau times delta x del t is equal to 0. So I'll write one more step for your sake. I'll write it a little faster. So negative m of x y dA over I minus integral minus m of x y dA over I, right? So This one I'm pretty much writing it into two parts. Minus dm y dA over I. This is also integral. So this one I split into two parts. One is for m of x, the other one is for dm. And because this negative is for both the terms, so I wrote negative here and negative there, and the whole thing here is in the parenthesis. Plus tau times delta x times t is equal to 0. So this term here cancels out with this term. So what we'll be left with is negative negative is positive. We get integral dm y dA over I plus tau delta xt is 0. So if we rearrange this, we get tau if we rearrange this, what we get is tau is equal to, so dm is not a function of area, y is not a function of area, I is not, sorry, y is a function of area, I'm sorry. Y is a function of area, but moment of inertia is constant for the cross section. So what I'm going to write is dm is anyways a constant for that cross section. So dm over I times delta x times t integral y dA. This is what we get. Then assuming, because for a thin cross section, for a really thin cross section, assume delta x is almost close to 0. That means we get dm over dx. This delta x becomes dx times 1 over it times integral y dA. What is dm over dx? Majority of you may have already forgotten dm dx. But I asked you, hey, remember, I'm going to bring this. Dm dx is nothing but V of x, shear force at that x cross section. So dm dx, I'm going to write it as tau equal to shear force at that x cross section times integral y dA over it. And this y dA, each time rather than writing as y dA, we write it as it's nothing but q. What is y dA? It is nothing but moment of area. That is y dA. What is the meaning of moment of area? Tell me what is moment of a force. Moment of a force with respect to neutral axis. With respect to an axis, basically. That means with respect to with respect to with respect to this axis, which we call neutral axis, right? What is moment of a force? How do you write moment of a force? Force times distance, right? So moment of force with respect to neutral axis, if I ask you that, what would you say? You would just say that, hey, it is nothing but force times perpendicular distance from the neutral axis. Similarly, if I ask you what is moment of an area, yeah, it exists. Moment of an area with respect to neutral axis. With respect to neutral axis is area times perpendicular distance from the neutral axis to the centroid of the area. This is the distance from neutral axis to centroid of the area in consideration. So those whoever watched this video till this point, this is the perk you get. You get to understand this term. So this y, you will get to understand that y. What is the meaning of this term y? That's what you'll get to understand now. And that is the one that's the most confusing part in this concept. For example, let's take that there is this cross section. So on the left hand side it's attached, fixed. So here I'm asking you, so I think let me draw it big. So let's say that this is the cross section. I'm going to draw it big. This is a rod that is somehow rigidly attached to the left side. Then if I ask you what is the shear force here, if I ask you what is the shear stress at that point, not at the center, but what is the shear stress at that point? And I'll give you that, hey, this is V. That means the shear force acting on the cross section at some X is V. If I give you that, and by the way, you should get negative, right? I forgot to write a negative sign. Yeah, when we rearrange this, we get a negative, we get a negative. It's fine, we don't need to write a negative here because what it means is it's going down. Our Y is up and the shear force is going down. That's the whole meaning. It's fine even if you don't write negative because we know it's going down. Anyways, now, if I ask you what is the shear stress at that point, you would take area about that. You would take area about that. And the shear stress, and let's say this is the neutral axis, and let's say this is y. Let's say if that is y, listen to this carefully. You're patient enough to come to this point. Pay a little bit more attention. Is nothing but the shear force times YdA. What did I say about this y? Moment of area, which is nothing but distance from the neutral axis to the centroid of area in consideration. And why did we take this area? Because I asked you what is the shear stress at the point. You had to take area above that point. You had to take area above that point till the top edge. So you had to take all this area. So tell me what is this? What is this for this case? It is nothing but the distance between the neutral axis to the centroid of the area. Where is the centroid of that area of let's say semicircle or let's say an arc? Where is the centroid of an arc? I'm going to give you a set of formulas. Maybe the centroid is there. Maybe centroid of that cross section is there. Maybe. Then what I'm asking you is this would be, let's give a different name, y tilde. Let's give a different name, y tilde, because we get confused between y and y tilde. So the shear force is this y tilde. That means you have to have y tilde times whatever is this area. Let's call this area above y. A of y is area above y over moment of inertia of the cross section times thickness. What is the thickness? Thickness is from here to there. Thickness is from here to there. That is the T. So this is shear stress at Y. That is the shear stress at Y. So what you need to understand is what is the shear stress at Y is shear force in the cross section times Y tilde. Remember, Y tilde is not equal to Y. That is the perk you get because you watched the lecture till this point. Y tilde is the distance between the neutral axis to the centroid of the area. That is Y tilde. But what is Y? Y is the point of consideration. Y tilde is centroid of the area above the point of consideration. Y tilde is the centroid of the area above the point of consideration. So this is the point. Y tilde is the distance between the centroid of that area to neutral axis. So Y tilde is not same as Y. So the shear stress at a point is nothing but shear force. Majority of you will write this. Majority of you can find the moment of inertia. Majority of you can find the thickness. Most of you or 80% of the class knows what is area. Area is this A is the area above the point of consideration. Area is A is the area above the point of consideration, 80%, but only 30% of the class knows this. What is Y tilde? Y tilde is the distance between centroid of the area above the point of consideration to the neutral axis. If you know this, you can apply this formula. That is the theory. So that's why rather than writing Y tilde, so the formula in the textbook is simplified. It is written as VQ over IT. So what is Q? Y tilde times area at area above the point Y. Okay. I hope all of you understood till this point. If you understand this point thoroughly, problems are piece of cake. Otherwise, it'll be a hard, you'll face some hard time understanding these problems. So ensure you understand this concept again. Rewatch the video again, until you understand that this is V of X, Q is Y tilde times A is area above the point of consideration. Until you understand this point. Sometimes I will give you what is V. Sometimes you have to calculate V by making a cut at that cross section. So that means if I give you some kind of loading, some kind of distributed loading there. So, and I'll ask you, hey, what is happening to this cross section? That means you have to make a cut. That means you have to make a cut at that cross section. Then you have to find, oh, this is V. Depending on this W load I gave you, you have to find V. How do you find V? From shear force bending moment diagram. You find V of X at X. Then if I ask you at this cross section, what is the, let's say the cross section would look like a C. The cross section would look like a C. And I ask you, hey, what is the shear stress at that point? You have to do, or I don't give you a cross section like that. Maybe I give you an I. It depends. You have to apply the form. This is Y. So area above Y times the centroid to the neutral axis. That is Y tilde. times V over moment of inertia of the cross section times thickness of that cross section. Hope you understood this concept. Watch out the next video for application of this concept to some problems. Okay.